Yeah. Okay, cool. That's useful to know. Yeah, so I will be presenting on class conditional conformal with many classes. And this is joint work with my wonderful collaborators, Anastasio, Stephen, Mike, and Brian. So let's start with a motivating example. Let's say you're a doctor and you want to diagnose patients who may have experienced head injuries. And you have an ML algorithm that says, I can produce prediction sets that contain the patient's true diagnosis 90% of the time. So that sounds pretty great. So you decide to give it a try. So here are some patients. The first patient, the algorithm outputs the prediction set no injury or mild concussion. And same for the second patient. And actually, it just outputs that for all 10 patients. But it turns out, actually, this last patient, actually has an intracranial hemorrhage, so a very serious diagnosis. So what's happening here is that since most patients actually have no injury or just have a mild concussion, the model can just always output the prediction set that contains no injury and mild concussion and still achieve 90% accuracy. So from your perspective as a doctor, this is clearly not very useful. So what do we actually want in this setting? We saw in the example that it's not enough for prediction sets to have coverage on average across all patients. Instead, we want to have coverage conditioned on the true label. So what this means is that when we're faced with a patient that actually has an intracranial hemorrhage, we want with high probability that the prediction set contains that diagnosis. So to formalize this a bit, given a patient with features X and unknown diagnosis Y, we want to output a prediction set, which we denote C of X, with class conditional coverage. So what this means is that even when we condition on Y equals Y, we want the prediction set to be correct with high probability. Yeah, so can we use conformal prediction to solve this problem? And the answer is yes, but naive methods struggle with when there are many classes or limited labeled data. So when we're in settings where these conditions hold, we must be a bit clever. First we'll review conformal prediction a bit. So working in the split conformal setting, where we assume we have access to some sort of black box model, and we use this model, denoted F, to define a conformal score function. So an example is F could be like a neural network that outputs a vector of softmax scores. So then your conformal score function could just be 1 minus the softmax score for the class Y. Yeah, so then to run conformal, we need access to a labeled calibration data set, which is shown there in green. And we're going to apply the score function to these labeled calibration data points to get scores. And then we're going to sort these scores and take the 1 minus alpha, or the finite sample adjusted 1 minus alpha quantile of these scores. And we denote that Q hat. And then at test time, to construct our prediction sets, we'll plug in test values of Y. And for values of Y, where the conformal score function evaluates to be less than Q hat, we're going to include those values of Y in our prediction set. So any questions there? That's just, yeah, and feel free to stop me at any time if you have questions. Yeah. So a fact about standard conformal is that as long as your calibration points and your test points are exchangeable, you will achieve marginal coverage. So I'm going to review the proof here because one of the key ideas of the proof will inform the method that we ultimately come up with. So this assumption that our test points are exchangeable implies that when we apply our score function to our test points, those scores will also be exchangeable. And by definition of exchangeability, any ordering of those scores is equally likely. So in particular, for the conformal score of the test point, the probability that it is one of like the m smallest scores is equal to m over n plus 1. And in this case, we pick a special value of m that's equal to that value here. This quantity over n plus 1 is greater than or equal to 1 minus alpha. And we can see that by definition of q hat, this event here is equal to the event that the conformal score of the test point is less than or equal to q hat. And by definition of the conformal set from the last slide, this is equal to the probability that the true label is included in our conformal prediction set. So a key idea here is that all we needed for valid coverage is that our conformal scores are exchangeable. Yeah, so remember this, this will come back. Cool. So standard conformal is guaranteed to achieve marginal coverage, but you may think that, okay, like even if it's not guaranteed to achieve class conditional coverage, it may still achieve reasonable class conditional coverage. But we find that this is not true in general. So this is a case study on ImageNet using 50,000 calibration images. So we set our desired coverage level to be 90%. And when we evaluate the marginal coverage of standard conformal, we get very close to that, which is as expected. But if we look at things by class, we see a different story. So here is the class conditional coverage for images that belong to the water jug class. So this is actually above our desired coverage level, which maybe doesn't seem so bad. But then there are other classes, for example, the flamingo class, that achieves a very low class conditional coverage. So this means that of the images that contain flamingos, only 50% of the conformal prediction sets actually included the label flamingo, which is not very good. Yeah, so a naive way we can adapt standard conformal prediction to achieve a class conditional coverage guarantee is the following, which we call class-wise conformal prediction. So you take your calibration data and you split it up by class, and then you estimate a separate quantile for each class. And then when you construct your prediction sets, instead of just comparing against like the single Q hat, you compare against the Q hat that corresponds to the Y that you're testing. So this will guarantee class conditional coverage, but it will require a lot of data per class because of this first step here, where you have to split up your calibration data set by class. Okay, so let's compare the two methods we got over so far. So in these graphics, you can think of each circle as the data for a class. So what standard conformal prediction does is it ignores the class structure and estimates a single Q hat. So the benefit of standard conformal is that it's low variance because it doesn't do any data splitting. It has a lot of data to estimate the single Q hat parameter, but it doesn't have a class conditional coverage guarantee. On the right, we have class-wise conformal. So what this is doing is it's splitting up your calibration data by class. And as a result, it has high variance because you have some classes with very little data, but it does have the class conditional coverage guarantee. So we wanted to know, can we get the best of both worlds? Okay, I'm sorry.
When doing the class conditional calibration, do you have like different thresholds for different classes? Like how is what parameters changing for different classes? Because like at test time, you don't know the true class. So is your procedure requiring to condition on the class?
For class-wise conformal? Yeah, let me go back to that. So the way you construct the prediction set is like for each Y, so for like each class, you can compute the conformal score, and then you know what Y you plugged in, okay. So you compare against the Q hat for that Y. Yeah, that's a good one.
That's the full conformal version?
It's not full conformal.
So you have a different threshold for including in the set.
Yeah, yeah. That's a good question. Any other questions? Yeah.
I have a question. So when you said in the class Y's case, so you use basically then choose all of the Ys which like cover the class-wise thresholds as well during your test time. Your test time we don't know what Y is.
Right, you don't know what Y is, but like, let's say like you have like 10 classes, so then you like plug in all of the possible Ys. You would plug in like Y equals class 1 and then see what the conformal score is, and then you compare against the Q hat for that class. Yeah, so actually like you don't need to know what the true Y is to construct the conformal set. Yeah, and the guarantee that this achieves class conditional coverage like comes from the same argument that we went over for standard conformal. Like you'll have exchangeability conditioned on the test point being in a certain class because you're computing these like class specific Q hats. Okay. Cool. Yeah, so our method, which we call clustered conformal prediction, tries to combine data from classes that are similar so that we get the benefit of like data sharing, but we also get a class conditional coverage guarantee. And I will go into more detail about what we mean by similar in the subsequent slides.
And low variance means that like in one experiment, one calibration set, the variance of the coverage, the actual achieved coverage would be high, or what's the effect of variance on the whole procedure?
Yeah, like so you can think about the cause of the variance is just like small sample size. So like it just means like your Q hats will be very volatile if they're estimated on little data. So that's the case often in class-wise conformal.
With respect to the randomness of the calibration set as well. That's why variance is important.
The guarantee is, it's like the standard like guarantee for
Yeah, I
like
mean,
conformal.
like because we have very few samples per class, your actual achieved like coverage for one realization of the calibration set will not necessarily be like the 1 minus alpha that you are going for, because the guarantees with respect to the randomness of the calibration set as well.
Correct. Yeah.
So that's why like variance.
Yeah. Good question. Okay. Yeah, so just to describe our method a bit more formally, we're going to assume we have some clustering function denoted H hat, which maps from a class to one of M clusters. And then I use this notation of Q hat of M to denote the conformal quantile computed using the calibration data in cluster M. So to compare this to class-wise conformal, the Q hats were computed only on data from one class, but now we're computing on data in a given cluster, which contains data from multiple classes. And then to construct our prediction set, what we do is we plug in a putative Y and evaluate the conformal score function, and then we compare it against the Q hat for the cluster that class Y belongs to. Yeah, and then I'll describe more about how we design H hat. But any questions on that so far? So for any clustering function, we'll get cluster conditional coverage. And the argument for this is just the same as the argument for coverage for standard conformal, because we have exchangeability between the points in a given cluster and the test point if we condition on the test point being in that same cluster. But remember that what we really want is to get class conditional coverage. So instead of conditioning on the test point being in a given cluster, we really want coverage condition on the test point being equal to a given class. So when does cluster conditional coverage imply class conditional coverage? So it turns out that if we have a clustering function that can group together classes in such a way that all classes in the same cluster have conformal scores that are exchangeable, then cluster conditional coverage will imply class conditional coverage. So in other words, we want to group together classes that have similar conformal score distributions. Does that make sense?
Is this not incorporating in any way the samples?
Sorry, is this,
Not incorporating the samples, because what if like some classes have like very few samples and some have like more samples? Will this exchangeability ensure that we're not like making vacuous bounds for any particular class?
what do you mean by vacuous
I mean, like,
bounds?
what if, because the samples are too low for one particular class, we have like scores in such a way that we just include, like, let's say, a lot of classes, or the score is like too low, or something like that.
So the proof of this proposition, again, just comes from the same exchangeability argument, because like if the data points you're using to compute Q hat are exchangeable with your test point, you will get coverage. Yeah, I'm not sure if that answers your question, but maybe I can continue and see if any of the following slides get at that. Yeah, so just to overview our whole method. Yeah, so we start with our calibration data, and we'll split it into two parts. One part will be used for clustering, so for figuring out what H hat should be, and then the other part is set aside for conformal calibration. And then using this clustering data, we'll again split it up further into data by class, and we'll run our clustering procedure to get the class cluster assignment. So this is just H hat. And then going back to the conformal calibration data, we'll also split this up by class initially, but then combining this with our class cluster assignments, we can then group together data from certain classes. So now we have like more data per cluster than we did like per class. And then we just do the standard conformal calibration procedure to get a Q hat for each cluster. So question you have is, what if we don't have perfect exchangeability within clusters? Because it's hard to design a clustering procedure to induce perfect exchangeability. This proposition says that even if the scores in a same class are not perfectly exchangeable, we will still have an approximate guarantee where now instead of having a guarantee that the coverage is at least 1 minus alpha, we have the guarantee that it's greater than 1 minus alpha minus epsilon, where epsilon is a bound on the Kolmogorov-Smirnov distance between the score distributions of classes in the same cluster.
Can you just go back to this one? That was read.
So are you clustering completely independently? Like, what's the objective of clustering? Objective function for clustering?
Yeah, so the objective is to cluster together classes that have similar score distributions. So the way we actually do the clustering is we compute like a vector embedding of each class. So yeah, and the specific vector embedding we use is like just the quantiles of the empirical distribution. And then we just run k-means on that.
Okay, so clustering the distributions of conformity scores?
Yes, essentially. So going back to this diagram, we like use this data to compute like the vector embedding.
Forces exchangeability.
Yeah. So just really using the idea of like clustering together classes that have similar score distributions.
And there is this epsilon arises that you only have like a random, you have an estimate of the CDFs of the score, so there's wiggle room for exchangeability not hold.
Mm-hmm. Yeah. Yeah, so moving on to some experiments. So we test on 4 different data sets using 3 different conformal score functions. So first, there's the standard ImageNet, which has 1,000 classes. We have CFAR 100, which has 100 classes, Places 365, which has 365 classes, and iNaturalist. And the particular version we are using has roughly like 600 classes. So these are all image data sets with many classes. Yeah, and the conformal score functions we use are softmax, APS, and wraps. And looking a bit more at the last data set I mentioned, iNaturalist. This is a really cool data set. It has images of like various like plants, animals, insects, and they're all gathered by like regular people and like uploaded, which is cool. You could also take photos and upload it if you want. So like some images are pretty like crisp and clear and like easier to identify. Others like contain like human hands or like really far away or blurry. So it's a pretty challenging data set because there are a lot of classes. Actually, just to give you a sense of how many classes there are, I put them like in the background of that slide. So there are a lot of classes. And there's extreme class imbalance because of the way that like these images are being gathered. They're gathered by like normal people who just like happen to encounter whatever like plant or animal they see. The most common class in this data set actually has 275 times more images than the least common class. So yeah, definitely a challenging setting. So we consider a few metrics. First metric, which we call cuff gap, is designed to measure like how good is your class conditional coverage. So specifically what we do is we compute the class conditional coverage for each class and then see how far it is from our desired coverage level of 1 minus alpha. And we average across classes and multiply by 100 just for readability. Yeah, so there are a lot of plots here, so I'll try to walk through slowly. Let's look at this top left plot. So here, the green line is our method. The blue line is standard conformal, and the orange line is class-wise conformal. And lower is better. We want a lower cuff gap. And on the x-axis is essentially the size of your calibration data set. So specifically, an average here denotes like the average number of calibration data points per class. So what we see here is that when we only have a few or just a small number of calibration data points per class, clustered conformal does much better than the other two methods. And as the number of data points you have increases, the performance of class-wise will eventually catch up to clustered conformal because you no longer have the problem of not having enough data to estimate Q hat. Yeah, so this, the first column is for the softmax conformal score, second column is APS, third column is wraps, and then by row, it's like ImageNet, CFAR, and then Places 365 and iNaturalist. And we see similar trends across all of these different settings. Yeah, so I'll let you guys spend a couple more seconds looking at that. So another metric we care about is the average size of the sets, because if you have prediction sets that have good coverage but are huge, they're still not very useful. So that's what we're looking at here. So same format essentially, except with a different metric now on the y-axis. So what we see here is that the class-wise prediction sets are huge when you don't have a lot of data. Meanwhile, the standard and clustered prediction sets are roughly the same size. So we see that our method clustered achieves good set sizes while also getting good class conditional coverage, which we saw on the last slide. Yeah, and I'll point out like one problem that we see for iNaturalist in particular is that like the class-wise prediction sets are especially huge. And this happens because of the extreme class imbalance. So when you try to run class-wise, you'll end up with like Q hat Ys that are actually infinite because you just didn't have enough data to properly estimate the finite sample adjusted quantile. So you always have to include those classes in the prediction set. Okay, and then the final metric we'll look at is essentially looking at the fraction of classes that are severely undercovered. So what this means is, since we're using a desired coverage level of 90%, this is the fraction of classes that have class conditional coverage less than 80%. So that's shown here. And we see that, again, like clustered is doing better or like as well as both standard and class-wise conformal for most data sets. The exception is in this last row, iNaturalist, class-wise has a lower fraction of classes that are severely undercovered. But if we look at this together with the last slide, we see that actually the reason this happens is because the set sizes are so large. So even though it's doing well in this metric, it's still not a very useful method because you just end up with huge set sizes in order to like achieve this good metric here.
Is there a metric that one could come up with to kind of see what's in the sets? Because like the way you present an uncertainty set of the same size to like a decision maker, wouldn't it also matter what's in the set if they are like classes that are actually similar versus classes that are all over the place? I don't think there's a metric for this, but is there a way to that?
Huh, yeah, that's interesting.
I mean, ImageNet, there's a hierarchy of classes.
Yeah.
You can use that.
That's what I was thinking also. Yeah, I'm not aware of a metric. I'm sure like
I don't think
probably you could construct one or maybe one exists, but yeah, that would be interesting to look at. Yeah.
How big are the clusters generally when you're doing this procedure, and how much does that vary across like the different functions you're using and across data sets?
Like how many classes are in
Yeah.
each cluster? Yeah, that varies a lot. And sometimes there's also like imbalance between cluster sizes.
Sure.
But I think like roughly maybe on the order of like 5 to 15. Yeah. And it does vary. One thing I kind of glossed over is in designing the clustering function, like one thing you have to set is like the number of clusters you want. So we set that in a data dependent way. So dependent on both like the amount of calibration data you have and also the number of classes. So you can choose K. So if you choose like a smaller K, you'll have more classes per cluster. If you choose, and the opposite is also true. But we did do some sensitivity analysis, and I can show you a plot later if you're interested, that shows us that it doesn't really matter that much what K you choose. Cool. Yeah, and then just kind of based on the last couple of slides and experiments shown there, we can come up with some recommendations for practitioners. So given a particular problem setting with like a certain number of calibration data points and a certain number of classes, like what is the best way to produce prediction sets that have both good class conditional coverage but aren't too large to be useful? So if you have very, very few examples per class, you should just run standard conformal because like clustered actually can't even help you there. It's a very difficult problem. So just run standard conformal and hope for the best. Conversely, if you have a lot of data, so this means at least like 100 examples for every class, then running class-wise will actually do very well. But in many real world settings, we're actually going to end up in these like intermediate regimes where we have a low amount of data per class, say like 20 to 75 data points. So clustered will do better than both standard and class-wise in this setting. And also in high data regimes where you have high class imbalance, clustered will do better. If you have low class imbalance, then you can run class-wise conformal in these settings also. Yeah. And just to summarize what I talked about today, first, marginal coverage is not enough. As we saw in the opening example, in some settings, we want to have class conditional coverage. But class conditional can be hard to achieve when there are many classes and limited data per class. And our solution to that is to cluster together classes with similar score distributions. And this allows us to share data between classes in a way that still allows us to achieve good class conditional coverage. And I think one extension of this work potentially is generalizing this clustering approach to achieve group conditional coverage for any sort of grouping. So in our work, we're aiming to achieve class conditional coverage, but you could aim for like different sorts of conditional coverage where you're like grouping based on groups in X space, for example. Yeah, so that's all I have. Feel free to check out our paper for more details or play with the code yourself. There's the code that I wrote, and then there's also a PyTorch implementation that people at SUS Tech wrote up. So yeah, thanks for listening.
So the enforcing exchangeability objective, you wouldn't need this if you have like completely pre-specified clusters and you want coverage per cluster. Is this because they are learning with clusters as well, or like it's also data driven that you need to?
Yeah, so like if you already have clusters that you want cluster conditional coverage with respect to, then you can just you can run that procedure. But that in general won't give you class conditional coverage. So it's just dependent.
I think of like if you want to use the same idea to do like conditional coverage in feature space and like cluster the X instead of like doing output conditional calibration.
Yeah, I think yeah, you can adopt the same idea of trying to group together like try to cluster together groups that have similar score distributions. That way you can like have more data for each like Q hat estimation, but still achieve the group conditional coverage you care about. Yeah.
Yeah, I think one data set that you might be interested in looking at if you want like a clinical application. I was just talking to Jivat about it. It's a skin condition classification data set called Fitzpatrick 70K.
Okay.
There's a lot of dermatology conditions. It's like I think 200 or 300. Yeah, there's like 17K samples, and there's actually like a fairness angle to it because there are people with different skin tones, and there are apps that people build to like automatically diagnose like dermatology conditions based on self-taken images, and these are not working very well for all skin tones. So you can need some form of conditional coverage. It's not exactly class conditional, but you can like conditional calibration is needed for like fairness reasons, not necessarily uncertainty reasons. And it's a large class, like large output space data set. And it's a difficult problem because I think even the labels there are not like super cleaned up. Like there's like there's ambiguity on what actually skin conditions people have.
Exactly, like I feel like that I can share the paper as one paper on it, but they've done with a modified like Monte Carlo conformal prediction, but the problem they deal with is that the ground truth itself is like ambiguous because like so many people annotate it, and then the people who annotate also are not sure like what is the diagnosis. So how do you ensure coverage while taking into account like the ground truth can be ambiguous? So like not dealing with just like one ground truth, but seeing how, because they actually showed, I think, I don't know what they said, but like with synthetic examples that you might actually be like you have a true distribution of your over classes and then over like what the ground truth is. And if there's like a shift, then you're like miscovering on the true class, but like your label is not the true class, there's like a distribution. So it's pretty interesting.
I think David Stutz has worked
yeah,
with this, right?
That's what the next talk will be about, which you should join.
Yeah.
But their goal is different. I think the data set itself can be useful, real application for something like this. You have like, because it's not usually the case that you have many classes in medical data sets, you just have like few conditions. But this is an example where like there's like hundreds of possible conditions.
Oh yeah, I'll check it out. Yeah, definitely send me the paper.
One other thing that I was thinking about is adaptivity, like the size of the set for each prediction. I'm assuming that you have like a fixed size set, or is this changing by like, is there something that makes the sets different for each prediction instance? Because sometimes you really want just a measure of uncertainty, not necessarily a coverage, so like a set that covers the true label, because you want to do like selective classification or something. You want to differentiate between high uncertainty and low uncertainty instances. So does this procedure like lead to different sizes of the prediction sets for instances, or?
In general, like the prediction sets will be larger than standard conformal. Yeah, because like in order to get the class conditional coverage guarantee, like you need to
Yeah, I mean,
include
like,
more examples.
will the set size be different for different predictions? So there is like in regression, there is like conformal quantile regression where you have like initial interval and then you can calibrate that. So you have different sizes of the prediction interval for each prediction. You're kind of trying to estimate the conditional quantile of the
Yeah. I don't know if there's something analogous in classification.
Yeah, that's what I'm asking. Even without class conditional coverage, is there can you do something analogous in classification? Because I haven't seen this also.
Yeah.
Sometimes like you really just need to get a signal on whether the model is certain or not like have a set per se.
Yeah, I'm not sure, but it's interesting. I'll think more about it.
How much did you iterate on the function to like define the clusters or H?
A good amount actually. Yeah, the one we ended up with is not the one we started with. Like, so we tried some other so what we ended up doing is like defining this like vector embedding and then running k-means on it. Like some other things we tried were agglomerative clustering. So like trying to group things based on actually their Kolmogorov-Smirnov distance between their distributions. Yeah, so we tried a few different things and then just ended up with it.
That one didn't work, given that was like.
Yeah, I don't actually remember why we abandoned it. I think at that time we didn't know like the problem with the agglomerative clustering is like you need to figure out like where to cut the tree to define your clusters, and we didn't have a good way of doing that. So yeah, but I think worth revisiting, because after we had written up the paper, we realized, oh, like if we had stuck with that original method, you can get like an end-to-end guarantee. Like if you cut like the tree at a certain so that like all the classes are within a certain KS distance, then you can like have the guarantee that like by running this specific method, you can have like at least a 1 minus alpha minus epsilon for some known epsilon coverage. But yeah.
Any other questions?